Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to focus on the difference between theoretical and experimental probability. And this is one of my favorite topics. I love probability in general, just because you can apply it to so many aspects of your daily life. And you can do that with a lot of different types of math, but I think probability especially, if you understand it, you'll just start to see things happening around you in a sort of a different light. And you may make your decisions a little bit differently if you understand, or if you have a good understanding of what probability is and are pretty good at calculating it. Let's jump right into this introduction problem. It says Dixon and Stacy are having an argument. Dixon flipped a coin 10 times and the coin came up head 7 times. Dixon says the chances of the next flip being a head were 70%. Stacy still says it's 50%. Who do you think is correct? Explain your thinking. So take a moment, pause the video, and write down your thoughts. Who is correct here? Who do you think is correct? Okay, so assuming our coin is fair, right? Assuming that's not weighted more on one side, or it's not some type of special trick coin, each flip of the coin is going to be 50% heads, 50% tails. It doesn't matter what's happened previously. Right? It doesn't matter that it's come up heads more times in the last 10 flips than tails. The next flip of the coin is still 50% heads versus 50% tails. Right? It's possible to flip a coin and you could take out a quarter, flip it. See how many times it comes up either heads or tails in a row. Right? You may flip a coin 5 times and it may come up heads all 5 times. Theoretically, you could flip a coin 100 times and it could come up heads. Now, if that happened, you'd really want to look into what type of coin you're flipping, because the probability of that happening is super, super small. But if you flipped a coin an infinite amount of times, you would see a string in there, landing on heads 100 times in a row, just because it is possible. So even though it seems like it's more likely to be heads because that's what's happened in the past, most recently, we don't want to have that bias. And we'll talk a little bit about how, we do live in Las Vegas, so people do like to go to casinos and play the different games and gamble. And we'll talk a little bit about, how we can apply probability to those games and why, those games are, going to be good for your wallet or going to be bad for your wallet. And that's something we should probably know, right? If you live in a city where you're surrounded by, that atmosphere of, people trying to play different card games or, roulette or blackjack for money, you kind of want to know if the odds are in your favor. Not to quote the Hunger Games, but you want to have that knowledge going in, so you know whether it's going to be a profitable investment for you or an unprofitable investment. Let's look at a little bit more vocab. I know we touched on this a little bit in our last lesson, but we also are going to add a few new words here. Probability. So probability, the measure of how likely an event is to occur. Now we'll talk a little bit about this later, but probability is not the same as a percent. Probability is going to be a number between 0 and 1, and we can convert that to a percent. So let's even write that. A number between 0 and 1. If the probability is 0, well, that means it's never going to occur. If the probability is 1, it means it will always occur. But generally, it's going to be a decimal between 0 and 1, or a fraction between 0 and 1. If you want to get a percent, then you would just end up multiplying by 100. But a true probability is not a percent. It's going to be a number somewhere between 0 and 1. An outcome, a possible result of a probability experiment or situation. Sample space, the set of all possible outcomes. So if you thought back to our lunch example from the previous lesson, the sample space would have been all the possible choices of one entree, one side, and one drink. Like pizza, coleslaw, milk, that would have been one outcome. And if I listed all of those different outcomes, that would be our sample space. An event is an outcome or a set of outcomes. So while the sample space contains all the possible outcomes, an event could just be a few of the outcomes, right? It's going to be between one and all of the possible outcomes. Equally likely outcomes, outcomes that have the same chance of occurring. You could think about it if you had a dice, should be die, believe. Dice is plural. Although actually I just went and looked it up real quick, and dice is acceptable as the singular version. You could say die, you could say dice if you're talking about one, but dice is acceptable, so I will leave it. Favorable outcomes, these are the outcomes in a specified event. So let's say you needed to roll, let's say somebody gave you a dice, and they said, I'll give you $20 if you can roll a 3 or a 4. Well, your favorable outcomes would be a 3 or 4 because you would earn money if you rolled those two numbers. Theoretical probability, that is the ratio, the ratio of favorable outcomes to the total number of outcomes. So down here, here's our first formula. The probability of an event occurring, that's what that P in parentheses event means. The probability is the number of favorable outcomes to the total number of outcomes. And we're going to work with this a lot as we move through not only this lesson, but the rest of this unit. Let's do one practice problem to show you how that formula comes into play. It does say we're going to round all answers to the nearest hundredth if necessary. So the first one says a CD has 5 upbeat dance songs and 7 slow ballads. What is the probability that a randomly selected song is an upbeat dance song? Well, think about that formula up above. The event that we want to occur, right, the favorable outcomes, are any of the 5 upbeat dance songs. Well, we need to compare that to the total number of outcomes. So pause the video, see if you can do that. You can leave your probability as a fraction, as well as give me the rounded answer to the nearest hundredth, if it is rounded. Well, the probability of an upbeat song, the number of favorable outcomes, and I'm going to write this ratio out the first couple times we do this. It's the favorable to the total. Favorable is 5. There's 5 songs that would be considered upbeat. And there's 12 songs total, right? 5 plus 7. So the probability of choosing an upbeat song is 5 over 12. If they wanted you to round that to the nearest hundred, well, 5 divided by 12, that would give us approximately 0.417. And again, just be familiar with both notations, whether it's fraction or decimal, and just be prepared to give what they're asking for. We are going to need to move on because we got a lot to cover today, so we're going to skip number 2 and number 3 and number 4, and we're going to move to complement. The complement of an event is the set of all non-favorable outcomes. The probability of the complement of an event is the probability that the event will not happen. Now, I feel like when we hear complement, unless we're thinking about somebody saying somebody saying something nice about somebody else, we may think complementary. It's obviously not the same here, right? Because we're not looking at 2 angles that add to 90 degrees. But we are looking at a relationship between 2 events, right? If we know the probability of one event, well, to find the complement, we would subtract that probability from 1. so the probability not E, and we're just letting E represent an event, would be 1 minus the probability of E. Let me show you, let me give you a little bit of a basic example before we jump into 5. Let me take a blank page here. So let's say we just roll a dice one time. Let me type this out, it'll be quicker. And we want to roll a 6. So the probability rolling a 6, well, there's 1 6, so that's going to be our favorable. There's 1 outcome that's good. The total number of outcomes, if we're thinking about a standard dice, or die, I'm going to say die. Dice just sounds, I know it's acceptable, but die just sounds better singular. There are 6 total possible sides, so the probability of rolling a 6 would be 1 out of 6. Now, the complement of rolling a 6, we just call that the probability not rolling a 6. Well, we could work that out, right? We know that there are 5 non-6 numbers, and there are 6 total numbers, so the probability of not rolling a 6 is 5 over 6. But we could also use this idea, right, that probability can never be more than 1, right? So the probability of rolling a 6 and the probability of not rolling a 6, those could never be more than 1 together. It's kind of like if I think about, and I will relate it to complementary angles here, it does have a little bit of an overlap. 2 complementary angles, right, we know they have to add to 90. So if one is 70, well, we're going to subtract 70 from 90 to get the other one. We know that together, they could never equal more than 90, right? They could never equal less than 90. Complementary angles have to equal exactly 90. Well, it's the same with the probability of an event and the probability of that event's complement. Together, the probability of the event and the complement will have to add to 1. So if I know the probability of an event, I can easily find the probability of the complement by subtracting the probability of that event by 1. So the probability of not a 6 is equal to 1 minus the probability of a 6. And that's where that formula comes from up above. The complement and the event, together those probabilities add to 1, so you can kind of do some subtraction there to find the other. All right, let's do one example. We're going to go up here and do a card deck example. So number 5 says, find the probability of not choosing a king out of a 52 card deck. So we use decks a lot for probability, just because there's a lot you can do with them. If you think of a standard 52 card deck, and let me just show you a visual. In a 52 card deck, you have cards that are clubs, diamonds, hearts, and spades. Clubs are the black clover-looking 3-leaf clovers on top. The spades are the black cards at the bottom. I think it's clear what diamonds and hearts are. Now, for each of those 4 suits, that's what we call diamonds, clubs, hearts, and spades, the suit of the card, you have the number denomination of the card. You can have an ace, a deuce, which is a 2, a 3, 4, 5, 6, 7, 8, 9, 10, and then you have a jack, queen, and king. So there's 4 different suits, and there's the same type of card in every suit. So if we go, and maybe you want to pause this and just study if you're not familiar with what a deck looks like, that's okay. If we go back here, we're trying to find the probability of not choosing a king out of the deck. Well, let's think about the probability of choosing a king, because then we can look at the complement. So probability of choosing And I get it, you could jump straight to the probability of not choosing a king, but because we're talking about complements, we're going to work that way. So probability of choosing a king, well, if we go back here, there are 4 kings, right? 1 for clubs, 1 for diamonds, 1 for hearts, 1 for spades. So favorable outcomes there's 4. The total number of outcomes, well, there's 52 cards in the deck, 13 of each suit, so 4 over 52. If I simplify that, that becomes 1 over 13. So there's a 1 in 13 chance that I choose a king. Well, using the complement, probability of, we'll just say no king, that's equal to 1 minus the probability of a king. So 1 minus 1 over 13, that's going to give me 12/13. That is the probability of choosing a card that is not a king. Again, just using the complement principle. Okay, moving on. Geometric probability, this is basically, we're going to apply theoretical probability to some geometry examples. We're not going to do this on the video. We're going to talk about it in class. But if you want to look at these, you'd be applying the theoretical formula, where we look at the favorable amount of outcomes, or in this case, we'd be talking about area, over the total amount of outcomes, or in this case, the total amount of space. So you would think about it as like favorable space over total space. If they gave you a volume example, you could do like favorable volume over total volume. But those are just kind of the examples we're going to look at as far as geometry goes. But we are going to jump down here to experimental probability. This is the ratio of the number of times the event occurs to the total amount of trials. A trial is each repetition of an experiment. And I know when you hear the word experiment, you may just think like biology class or chemistry class or some science class. But an experiment is purely something you're testing, right? We could call a flip of a coin an experiment, and each flip of the coin would be considered one repetition. So it doesn't have to be all science-y, quote unquote. I know that's not really a word, but it doesn't have to, you don't have to think about a science lab to think about an experiment. Mathematicians set up experiments all the time. They may just look a little different from science experiments. It says, think back to the coin example from the introduction. What would the experimental probability be of the next flip coming up as heads? What would the theoretical probability be? So, and this is a key difference. Experimental probability and theoretical probability, we do not find them the same way. If we think back to theoretical probability for the coin example, we'll do that first because we're already familiar. Well, we know that that's favorable number of outcomes over total. Well, if we're flipping a coin and we want to get heads, the favorable number of outcomes would be 1. There's 1 head side. And the total number of outcomes would be 2. There's 1 tail side. So the theoretical probability of getting heads on any throw would be 1 over 2, or 0.5. Experimental probability is a little different. So this is the number of times event has occurred over number of trials. So if we think back to our coin experiment with Stacy and Dixon, I believe those were the names I came up with. Out of the first 10 throws, heads came up 7 times out of 10. So 7 times heads came up, and there were 10 total trials. So the experimental probability was 7 out of 10. And you'll notice that's different from the theoretical. Experimental is purely based on what you already have seen. And you can see down here, while the experimental probability may not always be the same as the theoretical, we can use it to estimate what the theoretical probability would be. In this case, probably wouldn't be a very good estimate, right? We'd be saying that heads is going to come up 7 out of 10 times, when in reality it's going to come up 5 out of 10 times, or 1 out of 2 times. But let's look down here. What do you think will happen to the experimental probability if Dixon flipped the coin 100 times? What about 1 million times? Well, take a minute to pause. Think about what would happen with this number right here, the 7 out of 10, the experimental probability, if Dixon continued this experiment. Would that change? Do we expect it to stay the same? Do we expect it to go up, go down? What do you think? Well, the idea is, as we continue an experiment over and over again, the experimental probability will become closer and closer to the theoretical. So after 100 times, maybe the experimental is now 6 out of 10. And it may not be, right? It's possible it goes up, but generally, the more times we do it, the closer it's going to get to theoretical. If you flipped it 1 million times, we would see it get closer to 1/2. If we flip the coin 1 billion times, well, that fraction would be even closer to 1/2. And you could think about it as, and again, this is a calculus example. I like kind of giving you guys a taste of what you may be doing in a couple of years if you continue your journey, if you're on the accelerated track. If you flipped a coin an infinite amount of times, now of course you can't do that, right? Because you'd never be done flipping the coin. But if you flip it an infinite amount of times, the experimental would eventually become the theoretical. And this has to do with an idea of limits. If you look at what happens as we approach infinity with something, in this case, we're thinking about an infinite amount of throws of a coin, we could essentially say that the experimental and the theoretical would be the same after an infinite amount of throws. Again, just a little taste of what may be to come for you guys in a couple of years. This does lead into one important thing regarding a fallacy that many people have when they come to Las Vegas. Let me clear this. And I want to talk about the law of large numbers. The law of large numbers says that the experimental probability will tend to get closer to the theoretical probability as the number of trials increases. Well, that's what we just talked about, right? If we did 1 million flips of the coin, we would expect that 7 out of 10 to get closer to 5 out of 10, or 1 out of 2. If we did it 1 billion times, we would expect it to be even closer. Now, something happens when people go to a casino, right? They tend to have what we call this gambler's fallacy. And I don't know how familiar any of you are with any certain casino game. So I'm gonna break it down to a very simple example. And we're just going to use the coin example. So let's say there's a game in a casino where all you do is you flip a coin and you can place a bet. And you can bet $20 that the coin comes up heads, or you can bet $20 that the coin comes up tails. Now, let's say that on the side of the table, wherever you're playing, the casino has a little chart. And the chart looks like this. Oh, not T and F, T and H. And let's even make it more obvious. Well, and they do this with some games, right? They have a chart that displays what the previous outcomes were. In this case, we can see that the last 3 results were heads. The one before that was tails, then the 3 before that were heads, etc. So some people use this chart to kind of decide how they're going to bet. They may think, well, it's come up heads the last 3 times. We're due for a tails, right? If we think about experimental probability here, I did exactly 10 trials. That's good. Heads has come up 8 out of 10 times. Well, people are thinking, I'm going to outsmart the casino, right? I know that a flip of the coin is 1 out of 2. And I know this law of large numbers that says over time, that experimental probability, right? This 8 out of 10, the experimental probability should become closer and closer to the theoretical, which means if it's going to get closer to 5 out of 10 or 1 over 2, I'm going to have to start seeing some tails, right? If it keeps coming up heads, that experimental probability is not going to get any closer to 1 over 2. So they think, okay, tails is due. I should expect a tails to come up the next time, right? Because we've had so many heads previously. Well, again, this is what we call the gambler's fallacy, right? They're using prior data to influence their decision for the next outcome. But we know that if we just look at any single trial, it's 50-50, right? It's 1 out of 2 that it comes up heads or 1 out of 2 that it comes up tails. The law of large numbers does not say, right, if the last 8 out of 10 flips were heads, the next one must be tails. It doesn't say that. All it says is that if you look at a very, very large sample, right? So if it's 8 out of 10 now, and then you do a lot more flips, right? And that could be 1 million flips, 1 billion flips. Eventually, that 8 out of 10 is going to get closer to 5 out of 10. But it doesn't have to get any closer during the next couple of flips. It's going to get closer, again, if you think very, very long term. But most people playing the game, they just are thinking about the next couple of flips, right? Theoretically, they'd have to sit at that table for, a very, very long time to see that 8 out of 10 come down to 5 out of 10, right? Even if they sat there for another 100 flips, they're not guaranteed that there's going to be, more tails than heads. So something interesting. On some level, people think that they understand probability, right? They have this idea of, I know that a coin is supposed to be split evenly, 50% of the time it comes up heads, 50% of the time it comes up tails. But then they misapply that to a game and think that, well, it's come up heads many times before, it's got to come up tails to even itself out. And that's just not the case. It will do that over a very, very large number of trials. But if you look at any, small subset of trials, you're not guaranteed to see heads and tails come out to be the same amount. All right, so that is going to do it for today's lesson. I know, again, we hit close to that 30-minute mark, but I get excited talking about probability. And hopefully you're starting to see how you can apply this type of math to some circumstances surrounding you or surrounding the community that you live in. As always, enjoy the rest of your day, and we will certainly look forward to seeing you next time.